Separating policy from mechanism is a key design principle, design idea in operating system. So policy is likely, the basic underneath idea of separating policy from mechanism is that, when you're looking at the operating system code, any systems code, there is a unmoving, less changing part, and changing part for depending on the context. So if you can it's natural that separating these two. So mechanism is the part that less likely change it. So mechanism describe how things work, and policy is changed according to its context or application. So policy describe how, right? So policy is about policy is what should be done, and mechanism is how to do some operation. So in scheduler, typical mechanism is example of mechanism include run queue, context switch, or multi-core scheduling. This scheduling kind of code, and policy is talking about scheduling algorithm, FIFO, round robin, SAF, SCTF, and today we're going to talk about multi-level feedback queue. So these two things are separated. So one key things when you're talking about separating mechanism policy is that when you are running the code of mechanism, if you want to separate policy, mechanism called the policy as design of function. So the function is kind of replaceable according to its context. So don't kind of intermingle the code of mechanism policy. Cleanly separate as function. So mechanism functions for mechanisms, functions for policy. That's kind of custom rule, kind of well-known wisdom for separating policy from mechanism. We talk about high-level design ideas, and this is kind of mechanism for scheduling, and we keep talking about scheduling policies, right? So we are talking about these assumptions and the scheduling, the scheduler ideas, preemptive scheduling and non-preemptive scheduler, and when non-preemptive scheduler executed, so we're moving to FIFO. FIFO is typical, simple, and easy to implement policy. Okay, so we compute turnaround time. One of the most important, the problem of FIFO is this convoy effect, which describe one big task having a large CPU burst, blocked following walks, causing the average turnaround time is really large because of this convoy effect, well-known effect. And to avoid convoy effect, we talk about two scheduling policy: non-preemptive scheduler, which is called shortest start first, and the other one is shortest completion time first, SCTF. Okay, STCF, right? Shortest time to completion first. All right, and we discuss these two things, and I actually kind of bring up these two ideas, and then we are moving to the next level, scheduling policies. Okay, so before moving to round robin, let's take a look at this example. So, what is the I think I give you some kind of example of these two things. So let's look at this chip. So here are SAF scheduling diagram. So P at time 0, SAF task P1, process P1 arrives, and it starts executing in the CPU. This is case of single core. Single core case, only one core is just the P1 executed. At time 7, P1 execute its all-time burst, and SAF pick the task. Which one? Why P3 selected? Here. Why P3 is selected? Why? Because the remaining time is shortest. So P3 is selected. Then P2 and P4. P2 and P4 has same burst time, so it requires some tie breaking rule. So usually P2 arrive first, then P2 scheduled first. Okay, so they are equal, and P2 arrives, earlier than P4. So P2 selected and P4. That's SJF. Let's look at STCF. Again, SJF is non-preemptive. This one is preemptive. So preemption points, let's take a look at here. So first, at time 0, only P1 exists, so it executes. At P time 2, the P2 arrives. So STCF compare the time to completion of P1 and P2. What is time to completion of P1 at time 2? What is time to completion? P1, 5. P2, 4. Okay, so P2 selected. At time 4, P3 arrives. Okay, so again, what I'm talking about, the preemption happens. Preemption happens when new tasks are ready. So we are actually looking at this situation, right? So P3 arrives here. P1, time to completion 5. P2, what is time to completion P2? What is time to completion? 2. P3, obviously 1. So P3 selected. P3 finish its burst time, right? So again, so sorry, so moving back and forth. This event happened. Okay, so now after P3, at time P5, P4 also arrives. P4, 5. So P1, 5, P2, 2, P4, 5. So which was selected? Obviously, P2. So execute here. Okay. Right? Sorry, P4. So after finishing P4, P2 only has remaining time 2, so at time 7, P2 finishes task. So at this point, P1 remaining time 5, P4 remaining time 4. So P4 selected. Okay, and so after 4 times left, P1 execute ends. So that is STCF scheduling. So turnaround time, sorry. So in STF, turnaround time. P1. What is turnaround time of P1? P1 turnaround time, 7. Okay. P2 turnaround time. P2 finish at 12, but it arrived at 2. So 12 minus 2, 10. Okay. Oh. Okay, Hyunbin, I will I will get into your question later. Okay, good. P3, turnaround time. Arrive at, finish at 8, arrive at 4. So 4. P4, 11. Okay, response time. P1 response time 0. P2 response time, it start first scheduled at 8, but P2 arrived 2, so 6. Okay. P3 response time, likewise, 3. P4 response time, 7. Okay. So clear, right? All right. The STCF, P1 turnaround time, 16. Okay. Okay, 16. P2, simple, right? 5. Okay, and finish at 7, arrive at 2. Okay. P3, 1. P4, 6. Okay. Response time, P1, 0. Okay. P2, 0. P3, 0. P4, 2. Okay. So clearly, STCF showing much better response time. Okay. So that is the one question. Okay. So I think who asked the question? All right. So Hyunbin's question, I will copy and paste Hyunbin's question again. Let me say that I understand. So here are question. So for STCF, what happens for following scenario? If there is a task A and B, and task A sports time 7, arrive time 6. At B sports time 3, arrive at 6. Then A will have to wait until B finish, regardless of remain time complete or A finished before B starts. So if task B arrives in the middle of execution of A, but let's say here. So A sports time is 7 and arrive at 0. Okay. And B sports time is what? 6? 3, arrive at 6. So here at 6, what is A sports time? In the scenario 1, what is B sports time? Clearly B sports time 3. So which one is scheduled? A. Okay. So 7, A. Then B. 2, 10. That's the correct scheduling diagram. Is it okay? Okay. All right. So back. So that was, to practice some, draw diagram cases and, see the difference between SAF and STCF. Okay. So that is the comparison between SAF and STCF. What happens remaining burst time is equal. So usually it requires tie breaking. So if remaining time is same, then program usually run a tie breaking rule. Most obvious common tie breaking rule is the task arrive first. So likewise here, at this point, P2 having 4, P4 also having 4. So they are burst time same, but P2 arrived earlier. So using the tie breaking rule, P2 selected first. Okay. So that's the kind of equal tie breaking, right? So limitation of STCF. Sometimes we don't know the size of CPU burst ahead of time. We assume that the CPU burst time is known, but sometimes it's impossible to know. So in that case, we have to predict. I talked about last time, right? Using exponentially weighted average. So the next time is predicted by this one, and alpha is parameter. So how to put the past or put the current. you have to kind of adjusting the parameter value. That's configuration depending on the situation. So there's kind of moving average. And another important limitation of STCF is what? What is the critical problem? Oh no, overhead is also high. Fundamental problem. This STCF is starvation, where let's assume that your system having n total number of tasks. So while running the system, if when short time to completion task keep coming, then the task having a long time to complete keep delayed, therefore it causing starvation. Okay, so that's the common problem, and to avoid this starvation, here comes most general and well-rounded, one of the well-rounded scheduling called round robin policy are invented. So let's talk about round robin. So round robin, each run queue is treated as a circular FIFO queue. So round robin is a variation of FIFO. Okay, each job is given a time slice, which is also known as time quantum. So time quantum is usually a multiple of timer interrupt period. Depending on the situation, the operating system. Usually, some systems have very fine-grained time quantum, and some systems have 5 to 100 milliseconds. Usually, okay. So the idea of round robin is run a job per given time slice. Okay, then switch to the next job in the next queue. What is it? Next job in what? FIFO order. Okay, so in that sense, round robin is a variation of FIFO, but the task is not infinitely executing. The task scheduled are not using the entire CPU burst, only for a given amount of time. Okay, and there's a preemptive round robin, there's a non-preemptive round robin. Both are possible. Beware of that. Okay. Okay. So the most importantly, round robin does not incur starvation. Why? Why round robin does not incur starvation? Why? One mechanism actually allows no FIFO. FIFO is also some FIFO based order, but it always having some task having some fixed amount of task and yield scheduled out. So time slice mechanism allows kind of interleaving of tasks, which guarantee that no starvation. So let's take a look at the example. So round robin, having distinct characteristic compared to SJF. Round robin usually focus on this metric, response time. Typically, round robin has higher turnaround time than SJF and also FIFO, but it's much better response time. Let's take a look at it. So this is an example of a FIFO or SJF. So if the CPU burst is identical, then SJF and FIFO work same, right? So their CPU burst is same. They arrive at the kind of in this at time 0 in this order, okay? And again, usually the tie-breaking rule is the task arrive earlier. So A execute first, then B, C. So SJF scheduling result identical to FIFO result. So in here, turnaround time and response time is 60 average. I always kind of say that average turnaround time, average specify that. Response time is 30, but in round robin, let's say time slice TS is 10, unit of 10, then A execute for 10 unit and scheduled out. Then B, which is ordered, B in 5 for the next thing schedule, used 10, scheduled out. C. Okay. So after that, ABC is repeating. Okay, Dorun, good question. Yes, I will get back to you. So good question. That's kind of a valid, very valid question, and I will get back to you. So soon. So here, turnaround time of A is it finished much later compared to this one, so much longer average turnaround time. So job throughput is worse, but it's pretty good at response time. Average response time is obviously, time slice, usually in general. So round robin is good for server, desktop, like mobile phone. Which one? Desktop. So your cell phone, Android, Apple, I bet that they're using some variation of round robin. Okay. Right. Then next important question we need to discuss is the length of time slice is critical. Okay. Why the slice have response time as new metric? Sorry. So this is kind of, I just introduced earlier, but this is kind of audience, so it's not you. Okay. Focus on the metric is response time. So sorry for confusing. Same thing. So this length of time slice critical. So think about that. Shorter time slice. Clearly, this response time is so if time slice is 5, then what would be the average response time in this case? 5, right? Okay. 5. But if this longer time slice, so is this correct? 5, 0, 5, 10, 5. Yeah, right. Oh. Okay. And however, if time slice is longer, then it makes worse response time. But if time slice is shorter, the cost of context switch happens here and here. So shorter time slice indicating more context switch, which dominate overall performance. So the context switch overheads get higher. So longer time slice, okay, amortize this, the context switch in this longer time slice. So it's much less overhead from the context switch, but it costs long response time. How about turnaround time? Which time slice? Longer time slice having better turnaround time, shorter time slice having a better turnaround time. Which one? Longer has better ET. Right? So that actually leads to a kind of headache question. Deciding a length of the time slice present a trade-off. So good response time, better turnaround time, good response time, worse turnaround time, worse response time, better turnaround time. There's some kind of trade-off. So time slice, the length of time slice is usually parameter. So administrator run experiment and find optimal value by empirical. So that is kind of one role of system, administrator find the best value. So when you design, when system designer kind of implementing this policy, there are some kind of parameters. Okay, this parameter is configurable, but sometimes this parameter actually can exhibit this critical trade-off. So one thing I heard from many Samsung, Samsung has the system building system. They have tons of parameters. They have to tune it. So depending on the kind of parameter, the system performance varies according to different cases. So that's one headache, but it's very hard to kind of finding best parameters. Sometimes researchers using some machine learning, so put like a lot of kind of features and then predict the best parameters. That's one approach, but that requires some kind of experimental, empirical, analysis of what's better times. There's no like good answer, but we need a kind of range of parameters, implicit output of results like turnaround time and response time, right? So that's the thing. Okay, so someone actually asked a question about the time slice. This is the effect of time slice. All right. So is time slice equal to clock cycle of time? No, I actually say that in round robin, time slice is usually a multiple of time or interrupt period. Question: if round robin time slice is infinite, sufficiently large, then round robin is not equal, not approximate, equal to what? If time slice is time slice goes to infinite, then what is it? 5. Okay. All right. So that's kind of most important, the scheduling. So here still, so we design, as so scheduling is kind of most common, and every system requires some scheduling. So when you design a schedule, what you have to do, mechanism and policy. We're talking about very important 3 policies: FIFO, SJF, STCF, round robin. So these 4 are really important and most basic primitive. After that, someone's kind of, variate distributed FIFO, deficit round robin, work stealing STCF. They are kind of a more advanced scheduling policy, but they are all rooted on this basic principle for scheduler. Most basic, most important. Right? Then you can actually tune your scheduler according to your more advanced use cases, but that's basic thing. Right? So that's key thing. And let's look at some kind of scheduler in different perspective. So we can think about scheduler, or we can classify the scheduler for preemptive and non-preemptive. Also, we can actually look at the scheduler for priority-based scheduling and non-priority, priority-based scheduler. So priority-based scheduling is there are some kind of processes given static priority. So there are some kind of set of system calls to changing system process priority. Change or set processes or processes priority. Okay. If priority set, what scheduler does is choose a job with highest priority. In this sense, recall that in SJF, if in this case, if shortest remain time is identical, then what actually work as a priority? Highest priority. The first priority is shortest, remaining time, and the second priority, arrival time. Okay, so that actually kind of can think about the priority. There's the rule of the priority kind of embedded in each scheduler. So priority. FIFO, what is priority? Arriving time. And so this priority scheduler can either preemptive and non-preemptive. Okay, so preemptive priority scheduler, for example, SJF. Non-preemptive scheduler is STCF. So preemption, non-preemption, priority are different things. Okay, don't get mixed in. So even if high priority task comes, non-preemptive scheduler, there is some kind of time window that lower priority task executing, while high priority task is waiting in the run queue. So preemption and priority are orthogonal. Okay. Priority scheduling is called kind of fundamental, always kind of dark side of the priority scheduling is starvation problem. If there's endless supply of high priority job and no priority jobs will never run. Like SF, if short CPU burst tasks keep coming to the system and long CPU burst has no time to schedule. Starvation problem because the CPU burst remaining CPU time is priority in SJF. Okay, so starvation problem and priority scheduling always moving together. All right, so 5 points, no priority. I say, all right, what time is better? This is a more precise way to put it. So, okay, and STF, what's priority remaining? The first remaining time. Okay, then, what does priority mean in round robin? What does it mean? What does it mean? In round robin, what does priority mean? Fairness. Finishing sequence. Okay, so let's take a look at this example. Okay, so here, this is a round robin without priority. Okay, so we already look at, task. But, oops. So let's look at. So let's say this is our priority. Given, then draw the scheduling diagram of priority based round robin. So for time slot 10, which tasks are executed? Which task is executed? B. Okay, not A, B. Then what? Then who? A. Then C. Beware that someone actually confused that, oh, in the next time, B has high priority, so A executed first, B executed first. No, that does not happen. Okay, round robin has based on the fair. So priority. So what is the role? What kind of mean? What the priority mean in round robin? After expiring, after kind of allocating equal time slice, priority based, within a cycle. Yes, exactly. In this area is called epoch. Don't care about epoch. Epoch is kind of complicated concept, so don't get bothered. But let's say there's some kind of period. So this is called epoch. Priority is within epoch, within some kind of given cycle. So this is repeating. B, A, C. Again, B, A, C. So high priority task, better response time, better turnaround time. Okay, clear. So that is meaning in priority and in round robin scheduler. Okay, any other questions? Simple, right? So I want to kind of clarify, so someone actually think about differently. So I just kind of specify clarification of meaning of priority in round robin and different schedulers. Right. So far simple. And then let's make the case more complicated, more elaborated. So given that we are assumption 4 is task only execute CPU time, but let's make this assumption 4 relaxed. So a task may interleaving the CPU time, IO time, CPU time, IO time. So overlap computation with IO. Okay, so here's case will be example. when task A and B is interactive. Interactive is using both CPU and IO. B is only using CPU. Let's say these two systems are executed at the same time simultaneously in a system, to process simultaneously in a system. So this is kind of a typical STCF schedule. So A arrived first, say, and let's say A has short CPU burst, then B, then A execute first. CPU. But during this time, A never using CPU time. Okay, so waiting. Then A CPU burst, executing IO, waiting. CPU using CPU, IO burst, waiting. So after waiting this one, finishing task, B gets scheduled. Obviously, this scheduling method is stupid. So what is kind of desirable way for improving STCF? Clearly, how to improving your scheduler when assumption 4 is relaxed? How to do that? Exactly. So overlapping this time. So overlapping IO and computation. So plug in B, plug into B in the middle of execution of A is good. So for that one, recall that A goes to blocked, which means schedule out. Okay, so to overlap A and B, sorry, maybe I'm doing a lot. Because overlapping A and B, remember that this block state is required. So block means that learning system goes to blocked queue. Therefore, while system is blocked, the CPU is kind of, invoke a scheduler that's executed between while A is blocked, either preemptive or non-preemptive. Both cases, this blocked state, actually adding the blocked state guarantee this overlapping A and B, CPU time and IO time. Right, so that's kind of an obvious one, and this is meaning of overlapping, right? Okay, so that's all about basic basic discussions about schedulers around Robin, etc., and incorporating priority scheduler and incorporating IO. So here's kind of one observation. Final goal of this lecture is kind of what the general CPU scheduler, most common, most popular. So Linux also using this scheduler, general scheduler. So what is kind of general scheduler? I want to make a good turnaround time. And also, I want to minimize response time for interactive job. So let's take a look at what is the way to improving the turnaround time? What is the way to improving good turnaround time? What scheduler? Good turnaround time. STCF. But STCF has observation, so you cannot. I don't want to, clearly no observation. Obviously. STCF first, okay. Round robin having some wrong time slice, okay? I want to minimize response time for interactive job. What is it? What is it? Round robin with short time slice. So let's try to mix it. Okay. So that's one idea. We don't know how to do that, but that is made some kind of observation. Second, for SAF, STCF, we know runtime of each job, but this is not practical. So there's no priori knowledge on workload. There's no knowledge of priority. So what kind of scheduler does not require a priori knowledge? FIFO. And variation of FIFO what? Round robin. So it seems like an intersection is kind of going to round robin, right? But round robin itself is not achieve this goal, right? Depending on time slice, it's changing. So I want to kind of dynamically adjust time slice. Okay. But randomly select next step to according to time to complete. That's good. Your idea is called rotary scheduling. Rotary scheduling. We will not cover rotary scheduling in this undergraduate, but that's kind of one randomized kind of good scheduler for modify this achieving this kind of goal. So the 3 easy pieces, there's some kind of one chapter describing the rotary scheduler. If you are kind of understand more advanced scheduling technique, read the chapter, but it's not mandatory in the course. Good point. And also for that one, the scheduler has to learn the characteristics of job and making a better decision. How? Learn from the past to predict the future. So like in a computer architecture, branch predictors and caching algorithms. So that is kind of some observation, right? How I want to do this good turnaround time and kind of better response time, not relying on the prior knowledge. And to do that, we have to learn some characteristics, repeating tasks over and over again. That actually leads to one of the most popular, widely used in modern operating system called multi-level feedback queue. So multi-level, characteristic 1, feedback, characteristic 2, set of queue, characteristic 3. Okay, multi-level feedback queue. All right, so let's take a look at this MLFQ algorithm. So here's the deal. When you are first designing a scheduler, I will recommend first implementing FIFO. Why? Why I recommend you implementing FIFO? For example, when my graduate student comes to, oh, professor, I want to kind of implement this system. I want to kind of first implementing scheduler. So what should I do? And first implementing FIFO. Why? Easy. Super simple. Implement it, make it work. And I want to kind of make a better, my system better than how to improving FIFO usually. What is kind of best, good extension of FIFO? We done implementing at the complexity of some, then moving to round robin. So usually round robin works well, really well. So at that level, you can achieve your desired property mostly. Then I want to make my system more sophisticated, complex, more mixture case thing. Your system is uniform, your task is kind of similar, round robin is best. Simple, and that's the most cost-effective implementation of scheduler. But your system is mixture, short, task we're having short CPU time, long CPU time, and some tasks can actually kind of issuing the IO randomly. Then you can improve your system's response time and throughput using MLFQ. That is common, most common, evolution of scheduler implementation. That's kind of standard, all right? So MLFQ. So multi-level feedback queue, a number of distinct queues for each what? Priority. So MLFQ is a priority scheduler. It has priority. So meaning that it's queue having different priority. So priority scheduling between queues, okay? Between queues, high priority. So for example, when task here and here, which one is selected? Highest priority one selected. Within a queue, round robin. Okay, that actually kind of giving some interesting insight, right? So I want to make a set of queue, and each set of queue having different priority, and within this one round robin scheduler. Okay, that goes to this rule. So if priority A and B, definitely A run first. If A and B has same priority, meaning the same queue, then round robin. Okay, so priority depending on based on this observable behavior. What does it mean? So let's take a look. So if task keeps staying here, then task keep coming to here, then this task has no way to get scheduled, causing starvation. So basic multi-level feedback queue having this changing priority. So here's the rule. Typical workload having on, again, the MLFQ is targeting for interactive job, short CPU warning, and requires fast response time, and some CPU intensive job needs a lot of CPU time, don't care about response time. Okay. So that actually having some, this rule attempt. Okay, beware that this rule will be revisited for improving something. But for now, so here's the when job first entered a system, it placed at highest priority first, topmost queue. This queue. Rule 4. If job uses up its entire time slice, for example, let's say time slice is 10, and use up its all time slice of 10 in round robin scheduler, then it goes to, while learning, the priority is reduced. It moves one level down to lower queue. So if scheduled here, then use all time slice and demote it to next priority. Okay. And if CPU if task give up CPU before the time slice is expired using up. So for example, time slice 10, but CPU only having 8, the task only using 8 time unit, then it stays at the same priority level. No move down to lower priority queue. So that is changing priority. Priority goes down. Okay, so this rule 1, basic rule of scheduling, and this changing priority rule 3.4a for B is that define multi-level feedback. Recall that MLFQ is mixture of interactive and CPU. So time slice of higher priority is shorter, equal, longer than lower priority. What's the answer? Okay, I'll get back to you. Shorter, longer. So usually shorter. But in their textbook, it uses equal. Not that kind of great, but for simplicity, it using equal, but some Linux or some modern operating system having shorter. So shorter and equal, so depending on textbook, they use it, but longer doesn't make sense. Okay. Okay, so in rule 4b, it is using IO and is it using IO give up CPU? Yes, in case of IO, it's also including the case of giving up the CPU. Yes. Okay. So with this MLFQ, let's take a look. So there's a task of A, which is long learning, B, short learning, and C, very interactive task. Rule. So using this rule, when task A comes, and first A gets scheduled in high priority queue, low priority queue. Q high, Q low. And then A executed next time. B is not arrived yet. So A goes to is time slice. Let's say time slice is 10. So time slice of Q 10, 10, 10 for simplicity. But in different operating system, lower Q has longer time slice. But textbook and this example using the same time slice. Right. So executed. While B comes, where rule according to the rule, B is inserted Q0, Q1, Q2. Where? Q2. So who is scheduled? A, B is scheduled. Okay. Okay. So A is suspended and B terminated. Let's say at this point, then A gets scheduled. Okay. So B time slice goes here at B's CPU burst time is, let's say 20, then terminated. So now A gets scheduled. C arrives. A executed for time. At some point, C arrives. Again, C inserted with a very interactive task. So it only using some simple time slice and terminated. They executed. C is doing some CPU burst time and I/O, and A executed. So likewise, A do some short CPU time and I/O, and C has been short CPU burst. Then CPU burst followed by I/O, and while performing the I/O, A is scheduled. So that is kind of a landscape of what happens vanilla original MLFQ. So MLFQ, this seems like it approximates. It's not exactly the same. Approximate what? What approximate? Yes. It actually kind of mimic the behavior of SJF. So good response time. Get it? Okay. All right. Then problems. So looking at this diagram, what kind of problem you can imagine? Starvation. When starvation? Short interactive task where short learning job keep coming, then A has no way to get scheduled. So it actually kind of the priority down rule for some this operation, but still this MLFQ is similar to original priority scheduler, which is not free from starvation. So starvation problem. One more problem. What kind of problem you can imagine? This is a bit tricky. So starvation is obviously most kind of important things to solve. And what? Too much context switch? Okay. Let's say you may heard about this term of using. Exactly. Okay. Intentionally, I have a long CPU burst P, but it pretend interactive task. So given time slice 10, I just executed 8 unit and give up. I call it yield. Then next time it also get 10, give up. Using the 8, give up. So it keep remaining highest priority and having a kind of benefit. So exploit the features of MLFQ of using. Okay, so two important problems. Starvation first. Second, malicious user can game the schedule by relinquishing the CPU just before time slice expired. Likewise, I said. Okay, so that's kind of a higher percentage of CPU than others. And also, some application having changes behavior, so it's kind of one thing, but these two are well-known problem of MLFQ version 1. So let's fix it. First, how to fix starvation first? What's the idea for solving the starvation? How to fix starvation? Aging. Okay, so aging is one term, but more specifically, what does aging means in MLFQ? Okay, boosting priority of low. So far, what's the problem? MLFQ changing priority always going to downside, upside? Only downside. So what's the idea? Changing priority to upside. That's the idea. So that actually leading to this rule 5. After some time period S, which is also parameter, some parameter, let's say, some usually kind of multiple of time quantum. After some time quantum path, move all jobs in system to topmost queue. Okay, so this is called priority boosting. So to avoid the starvation, let's say A executed, and A executed, and A executed, and so forth. Keep going. After some period of time, then what happened? A is boosted. So when new task comes, okay, then you schedule and keep coming. Okay, sorry, it's describing the starvation scenario. Sorry, so making animation. So that is kind of typical. If this keep coming, starvation happens. To avoid that, a task executed and boosted. Okay, and execute task. Execute. Okay, so 3 time quantum is period S is 3 TS time slice. And after that, boosting. Going to high priority tasks. High priority executed. When new task coming, short task coming, okay, this is happen here. Okay, so this one, why this scheduling? Round robin. Okay, so we run round robin schedule here. Then if this task is terminated, then boosting into here, A is executed. So after sometimes 3 times slice, A is kind of boosted. So next time it's scheduled, A get boosted and up to. So here, after using time slice, A is moving to here originally, but boosted to here. Executed. Oh, is it 5? Depending on. So I want to say I'm saying the boost always happens from the Q0 to Q2. Lowest layer. Okay, so after executing 1, 2, 3 times slice, given time, I boost it. So if A spend 3 times slice here, A is stay here, and so boosting is a bit confusing. This time slice, say 3. It's not clear. A is never going to Q3. So here, let me see. Time slice 3, and A is never executed. So after 3 times slice, this one. Okay, you're right. I think in this case, time slice S is 4 multiplied TS, because here 1, 2, 3, 4 boosted. 1, 2, 3, 4 boosted. So likewise, after 4 times slice, boosted. Okay, Simon? Sorry for confusing. So that's more correct way to put it. Okay, is MLFQ's IO aware? Yes. Every round robin and MLFQ is IO aware. When IO happens, and then this scheduler can goes to block and the tasks who are actually kind of non-performing IO get scheduled. So yes. In the example, the time slice of each queue. So in the example, time slice, the time slice of each queue are same, right? Yes. Here, the example, for example, the time slice of each queue are same for explanation. But in reality, Q1 has lower time slice, but the example is same. Or otherwise, it's complicated. Like what's period, how to define the period. So for simplicity, I make this time slice kind of equal, and also textbook also follow the equal. But yes, so does the boosting solve the third problem as well? Third problem. What was the third problem? Oh, changing the behavior. Yes, I say yes. So the boosting also kind of help to address this changing behavior. The changing behavior is hard to predict, but if you kind of moving down in MLFQ, moving down in MLFQ, moving priority Q2 to Q1 implies what? Long running task. So looking at the past, it using keep CPU over and over again. So MLFQ learned that, oh, this task long CPU time. But at some point, A are changing to IO burst phase. So without boosting, that is not affected. But by boosting, this knowledge is reset and looking at it again. So in that sense, the prior boosting mechanism also help to address this changing behavior. So I mean, does it make sense? Okay. All right. You're almost there. Okay. So no. So second problem, that abusing problem, simple. The idea is that the task keep kind of relinquishing yielding CPU before time slice expire. So obviously, the way to solve is that it actually uses up its time allotment. So instead of time slice expired or not, just accounting of time. So accumulated time is beyond this time slice. Then likewise like MLFQ moving to down. Regardless of how many times it gives up the CPU, without that, it just kind of accounting the time using the CPU. So if accumulated time is beyond its time slice, then priority is reduced. Simple. So that's actually heading to this better accounting rule. For example, let's say this is kind of an abusing case, right? So without precise accounting, B relinquishing before time slice, relinquishing the CPU. But with that, if you're using the small amount of time, lowering to B and going to this way. But without just kind of if this sum of the CPU time is beyond time slice, right? Simple. All right, so that is end of the MLFQ. So it's just summary. MLFQ, this is kind of refined rule. First, this priority-based rule. Second, this highest priority rule. Third, better accounting rule. First, priority boosting rule. Okay, so that rule 5 is kind of in a summary of MLFQ. So again, the beauty of MLFQ, it does not require prior knowledge and high priority queue. If priority, short CPU tasks keep coming in short CPU burst and does not compete with the long CPU time, so that it quickly scheduled. And the task, if task having a long CPU time, and if there's no other task comes to system, it enjoyed in the last level, it enjoyed longer time slice to improving turnaround time. So MLFQ is pretty well-rounded for most cases. Response time and good turnaround time. So basic idea of MLFQ is kind of a sorting. of task and looking at some kind of over time. So if task is keep using time slice, MLFQ learn that, oh, that task has long time slice and move to low priority. Okay, so that is basic idea of MLFQ. Simple and beautiful. Any other questions? So MLFQ is kind of an ultimate scheduler, and I don't see any scheduler better than MLFQ in terms of generality. For specific use cases, better response time. There are some kind of tweaking for, good, using kind of, using SAF, exploit SAF, achieving the better response time. But in terms of generality, MLFQ is the king. How many prior levels there in real operating system? A lot. So in Linux, 156. Around, I forgot that. 150 around that. Oh, sorry, I forgot that. More than 100. Okay, so real-time priority, normal priority, etc. So there are a lot. Okay, so that actually we conclude, the scheduler. Scheduler is simple. Someone say scheduler is boring. Well, scheduler is one of the most basic system component. When you are working as a system engineer, the most frequent operation you are learning is schedule. Scheduler is kind of basic and kind of common. So originally, I prepared some kind of Linux case study, see the priority. So see the priority table. So this is kind of recap 40 more than 40. So this is kind of one class of priority. So that actually consists of several much larger priority in Linux. But I'm not talking about Linux detail. Sorry. Given the time limit, I cannot go through the Linux the MLFQ scheduler real implementation. Sorry for that. Okay. All right. So next time, let's move into memory. So I have only 7 minutes, so I need to explain this concept first. Memory. Okay. Changyong, could you please ask your question after finishing this lecture of initial lecture in memory, and then we will get back to your question soon. Right. So virtual memory. I say still, let's go back to this abstraction design. Same thing, right? But having a different principle. So virtual memory, what we actually kind of run so far. So this is user level program. This line indicates distinction between user and kernel, and there's a system call interface. System call is kind of exception. Okay, hardware also make an interrupt. So in this sense, we can see operating system is set of event handler executing from the system call, executing from the hardware events. Okay, so it's a set of event handler. What event handler works? So we're looking at the protection design. Okay, and scheduler. Okay, synchronization after VM. File system we never run after synchronization. So we are focused on today memory and device management a bit with the file system. Okay, so we run this one and this one and this one and this one. Okay, and some of IPC. Scheduler, we run that. Okay, so scheduler not yet, file system not yet, memory management not yet. So if you cover this one, then we actually kind of learn entire system operating system. All right, so good. So before going to memory, I want to introduce one important design idea. In my slide, usually I start before starting with some detail. I want to kind of introduce important design concepts. I think this is kind of most last thing. I don't think new design ideas except for this one. But okay, recall that. In scheduler, what we learned in the design idea? What design idea, high-level design idea we learned from the scheduler example? What was that? Separating policy from mechanism. Okay. Now, one of the super important idea of called level of indirection. Okay, so level of indirection. So this is high level, wisdom, right? So there's no concrete example. So still very vague, but let's learn the concept. Okay, so abstraction, separating powers from mechanism, level of indirection is three important things. Okay, all right. So indirection is this one. Let's say this is a function. Given the input, this information is translating to the other information. Okay, then there's a function, there's an important input translating. So level, what, by looking at this formula, what are levels? What is the levels? This information is translated, this information is translated. So what is the level? Level. Okay, what is indirection? Indirection, what does it mean indirection? This function. So usually a function can be, approximate some table, right? So function is just kind of a given input, output table. So this is a, indirection. Super vague, right? Okay, so what am I talking about? What does it mean? So there are popular examples of level of indirection. In the slide, always there's a picture. What is the typical example in level of indirection? In the slide, what? Pointer. Exactly. Okay, so there's a value inside pointer. The address of pointer doesn't have meaning. Okay, so there's a value. Is it real value I want to use? No. The value is what? Translated. Okay, and there's a real value. So here, what is level? What is level? What is level? Translate from pointer and value is value. What is indirection? What is indirection? Location of address, the relationship. Called T reference. That's the indirection. Good. So that is the level of indirection. So information semantic, address level semantic, address level information, value level information are distinct, and they are connected by this T reference operation. Level of indirection. Okay, recall, just kind of run from the, some bottom. Why pointer is useful? Think about it. Why pointer is useful? Why do you learn that you should use pointer? Passing argument is kind of one use cases, but what is the fundamental reason that pointer is useful? Why the point? Exactly. For same location, let's say one pointer value, two pointer value can pointing, position independent. Using different value, you can specify some value. Okay, so the value here, the value system here, level system here, this level system here are orthogonal. And if there's some kind of connectivity to here, using indirection, you can associate these two information. Linear algebra, exactly. In linear algebra, input is input matrix, output is y matrix. These are two level. What is indirection? Well, this translation matrix, implies this indirection information. So one domain are translating to the other domain, right? So that is level of indirection. Do you have a sense that why do I talking about level of indirection in virtual memory? Why? What does the level of indirection has to do with the virtual memory? Exactly. Virtual address, physical address, level 1, level 2, indirection by translation. That is concept of level of indirection. The virtual memory is about how to efficiently build level of indirection. Okay, so that's the rule. And we are looking about, this level of indirection of virtual memory next time. Okay, the key concept of virtual memory design is level of indirection. Okay, right? That's all for today. And let's talk about this, virtual memory lecture in this Wednesday. After Wednesday, we have long Chuseok holiday, and there are like a lot of the national holidays. We don't have much time to give a lecture for memory, but let's do it. And then probably next Wednesday, I will talking about some kind of some discussions of Pinterest quiz. Okay, so all right, thank you, and talk to you this Wednesday. Right? If you have any questions, feel free to ask. If there are Changyoung's question, if there are too many tasks in the top queue, it is not exhausted in Parades, so RR does not follow the predetermined rule. If there are too many tasks in the top queue in MLF queue, it is not exhausted. It's not exhausted in the period of S. So those still follow. Okay, Changyoung, your question. Yes, so QQ2. Q1, 2, Q3, 2. So given the time period S is just kind of 4 time slice, let's say. So I'm moving to here. And there are many task comes. After 4 time slice passed, A is promoted to A. So let's say A, B, C, D, E, F, keep coming. A is inserted. Now we have to run round robin. A has get chance to schedule in Q2. 0, 1, 2. So, but I'll still follow predetermined queue. I don't exactly understand your question, but after this period S, A is boosted to highest one. So computing with this other task with round robin. Round robin does not guarantee starvation, so A gets scheduled. Any questions? Any confusing questions? Okay, all right. So if scheduler SAF by default, if scheduler follows SAF by default, runs all new processes for very short time, then queues them again. Okay, some kind of check. Okay, yes. Then the average response time drops to nearly zero, while average turnaround time is relatively low. So let's say, I'm not, but I don't think it's good policy, even though it shows good metric. Yeah, I agree. So, yeah, probably I understand your question. So when run all new processes for very short time, okay, intentionally, okay, and then queue them again, yes, then average response time drops to near zero. Okay, pretty short. Okay, and average turnaround time remains relatively low. Yes, that's not good policy. But is there any that kind of thing, that kind of behavior? Does it giving any incentives to abuser? What is kind of benefit to abuser? So, for example, in MLFQ case, the abuser has kind of clear incentive that I want to stay in the highest queue, so that I want to use more CPU time than others. That's kind of clear goal for abusing the scheduler. In that case, what is kind of purpose? So reasonable attacker cannot do that way. Then attack does not effective. We can actually claim that. So I don't see any kind of benefit of who are actually kind of abusing. So I don't see the attractive incentive for attacker for that case. Is there? good question. I like this kind of, some angles that I did discuss, but yeah. So if you have, feel free to ask me. So I didn't see, clear benefit of attacker. The second question, if short tasks are come to the system, then new task goes to next epoch. If new short tasks are coming to the system, then new task goes to next epoch. Okay, Jihan, the definition of epoch is long, and there are many corner cases and confusing. So, for example, epoch is kind of really loosely concepted. Because of that, I didn't explain that. For example, tasks keep coming. While this task is kind of finishing, then how to define the epoch? So epoch is not very precise thing, so don't get bothered about epoch thing. Epoch is just kind of situationally well defined, but in some case very hazy definition of hazy. So that is the reason that some textbook not kind of use the term epoch in round robin. But yeah. So in general, you are saying is right. So when task is coming to system, then the task. So, for example, task A, B, C, D. While executing the D, no, sorry, you're not correct. So while round robin scheduling and D is remaining, when E arrives, then A, B, C, while executing the C, E arrives, then D and E, then that actually goes to epoch. That's by definition of epoch. So at the epoch can infinitely increase. But the thing is that the number of tasks in an epoch is fixed. So if you go beyond some number of tasks in one epoch, then the task is kind of counted to next epoch. That's kind of most heuristics of epoch definition. Does it make sense? But it's not kind of it's like ugly. All right. Okay. So the boosting period, it depends on. So the textbook actually say that but usually most implementation at the essay is per job. I will clarify later. Don't know. Good. Per job. Okay, other questions? Good. Okay, so thank you and talk to you this Wednesday. Bye.